Okay, so we're going to be looking at trigonometric integrals and mostly integrating expressions that have, tangent, secant, all these things, and trying to figure out how to handle that. Okay, these are some identities from, trigonometry that we should be familiar with. Here's one of our Pythagorean identities: sine squared x plus cosine squared x equals 1. And then here are two others that we might want to be familiar with. So the author does a really good job in the textbook of giving us a strategy for how to approach um, these types of integrations. So looking at the rules, I won't read them to you line for line, but when you go back through your homework, make sure you look at these because they tell you exactly what you need to do. So in this first one, notice that we have sines and cosines. And remember that sine and cosine, they're kind of derivatives of one another, right? Okay, except for a minus or whatever. But what they say is that if we have an odd number of cosines, what we're going to do is, or rather an odd number of sines, take one of those sines out to the side, and then we're left with some multiple of sine squared. Right? And I'll show you this in an example, but we can convert sine squared using this rule right here. Okay, and then that way we'll be able to go on with our manipulation for our problem. And here's a similar rule. If we got an odd number of cosines, I'm going to hold one of those. We're saving it because we need it to be our derivative. Okay, and then convert everything else to sines, and then we can integrate it that way. So that's how kind of most of the rules go. Here it says when the powers of both are even, then that's when we might use those rules there. Okay, so let's look at an example. It says find the indefinite integral, and we've got cosine cubed x sine fourth x dx. Okay, so what I'm going to do is, since I've got an odd number of cosines, I'm going to hold one of those to the side. So I've got the integral of cosine x. That leaves me with a cosine squared x and sine x to the fourth power dx. Okay? And using the Pythagorean identity, I can change cosine squared to what? Very good. Okay, so we got cosine x. I'm changing this to 1 minus sine squared x. And then we got sine to the fourth power x dx. Okay, so once I kind of distribute everything across these parentheses, we end up with the integral of cosine x sine to the fourth x dx, okay, minus the integral of sine to the sixth x times cosine x dx. Okay. And so I could let u be sine x, and then du is going to be what? Cosine x dx, right? That's true for both of them. If we say u is equal to sine x, then du equals cosine x dx. And so we don't even really have to write out all the steps for the substitution, but should I? Yes, okay. All right, so then this would be the integral of u to the fourth. Cosine x dx is my du, minus the integral of u to the sixth du. And of course, that's going to give me u to the fifth over 5 minus u to the seventh over 5 plus c, or sine x to the fifth power over 5 minus cosine, or rather minus sine x to the 7th power over 7, not 5. Okay, plus c. Okay, questions about that?
Did you distribute the cosine x to the 1 minus sine squared?
Yes, I distributed the cosine x and also the sine fourth x dx. So all of that got distributed across the parentheses. Okay. All right, other questions? All right, very good. All right, here we have sine 6 theta to the 4th power d theta. All right, and so for this one, notice in our rules, it says when both powers of sine and cosine are even and non-negative, well, we only have just the one. But it says we could rewrite that using sine squared x equals 1 minus cosine 2x over 2. This is the third rule on your paper there. So what I'm going to do is, first of all, write this as the integral of sine squared 6 theta. I'm going to square that, d theta. Okay, that still gives me to the 4th power, right? Okay, and then for sine squared 6 theta, I can rewrite that as 1 minus cosine of 2 times whatever my argument is right here. So this is the integral of 1 minus cosine of 2 times 6 theta. So that gives me 12 theta over 2. Okay, and then that's still going to be squared d theta. Okay, so I'm going to go on and multiply this out. So we get what? 1 minus 2 cosine 12 theta plus cosine squared 12 theta over 4 d theta. Okay. And then what might I do to deal with this? Some things you may or may not try today. Okay, distribute it, right? Because it could go to each of these things. So we're going to say equals the integral of 1/4 minus 2 cosine 12 theta over 4 plus cosine squared of 12 theta over 4 d theta. Okay. All right, so we distributed the 4 to each term in our numerator. Okay, and now we should be ready to integrate at least the first two parts, right? The integral of 1/4 d theta is just going to be what? 1/4 theta. Okay, very good. And then here we've got 1/2 cosine 12 theta. That's going to be what? If we need to, we can do the substitution. U equals cosine, let's see. What do we want u to be equal to? Sorry. U could be equal to 12 theta. Okay. So du is going to be 12 d theta. So we're looking at the integral of cosine u, and then we need to do du over 12. Okay, how do we integrate that? Okay, we can pull out the 12, or 1/12. The integral of cosine u is what? Is it negative sign?
No, it's just sine.
Okay, sine. Okay, very good. So we get 1/12 sine u. So we got 1/2 times 1/12 sine 12 theta. Okay, and then for this piece, it's still squared. So what we're going to do is apply the special formulas up top again. Okay, because we want to try to get it down to the first degree. So we still have plus the integral of cosine squared 12 theta over 4 d theta. Okay, and if I apply that formula again, it says cosine squared x is equal to 1 plus cosine 2x over 2, right? So I can change this to what? 1 plus cosine 24 theta, okay, and it's already over 4. We can pull that 1/4 out, okay, this goes over 2, okay, d theta. Okay, and so now we get plus 1/4. Okay, the integral of 1/2 d theta is going to be 1/2 theta. The integral of cosine of 24 theta over 2 is going to be what? If we kind of use the same pattern over here, we're going to get what? Going to be sine 24 theta over 24. Okay, plus c. All right, so if we put all that together, we've got 1/4 theta minus 1 over 24 sine of 12 theta. Okay, and then we got plus 1/8 theta plus, what's 8 times 24? It's what? Okay, which is 192. Okay, so we get sine 24 theta over 192 plus c. Okay, questions about that? I could have pulled a 1/4 that, but yep, that works. Okay, good. We can combine these two terms. So 1/4 theta plus 1/8 theta would give us 3/8 theta. Okay. All right, questions. Okay, very good. All right, we've got another one. Notice here that beneath our radical, we've got sine, okay, and that's kind of hard to pull that one out. So we might want to think of converting, holding on to a cosine to be part of our derivative, and then changing everything else to sine, okay? So the way we're going to do that, okay, first of all, I'll rewrite this. I'm going to take off a cosine for my derivative. So cosine t, then I've got cosine t to the 4th, okay, and then I'm going to write sine of t to the negative 1/2. I could have put the negative 1/2 there. Let's put that there. And then dt. Okay. All right. So um, I've already got my derivative present, cosine t dt, if I can change everything else to sine. So I could rewrite cosine fourth or cosine t to the fourth as what? Sine square t squared, right? Okay, and then we got sine to the negative half of t dt. Okay, so I'm going to distribute, oops. Well, first, before I can distribute, what do I have to do? I've got to actually square that, right? So we've got the integral of cosine t. I'll go ahead and pull that sine to the negative 1/2 t over here, and then I'm going to square this out. So it's 1 minus 2 sine to the 4, or sine, 2 sine squared t plus sine to the 4th t. And then we've got our dt. Okay, everybody with me? All right. And so I can distribute this to each one, and we get the integral of cosine t sine to the negative 1/2 t dt minus 2 times the integral of sine to the 3/2 t cosine t dt. All right. And then plus the integral of sine to the 7/2 t cosine t dt. Okay. But for each of these, we conveniently have cosine t dt present, which is the derivative if we let u be sine t. All right. Is that okay? So we don't even really have to do the substitution, but I'll write it just kind of in general, just for the record. We're going to say u is equal to sine t, and du is equal to cosine t. Okay, and we've got exactly that for each of these. So this will be what? If I add 1, it's going to be sine to the 1/2 t. Over here, we're going to get minus 2 cosine to the what? 5/2 t. But then I'm going to have to divide by 5/2 or multiply by 2/5. Okay, and then over here we get plus sine to the 9/2 t. Okay, divided by 9/2 or times 2/9 plus c. Okay. Okay, questions about that? Let's see. Let's see. Right here. This should definitely be sine. Hold on, let me change that. Wow. think the opera next door is distracting me. Okay, this is sine to the 5 has that sine. Okay, now what was your question?
You added 1 to 1/2.
I added it to negative 1/2. And so we got positive 1/2. Okay. All right, other questions? Okay, so this seems doable, right? Okay, all right, we're just gonna have to have some practice. All right. Okay, well, let's revisit that integration by parts we talked about last time. Um, and we kind of came up with this um, scheme for how to approach these things or what we should let be u. And so we said that u, the algebraic expression, comes before trig. So let's let u equal x squared. And we need a lot of space. Let's see. Okay. All right, so u equals x squared. Then dv is going to be sine squared x dx. Okay. Du is going to be 2x dx. Okay. And v, well, we got to do a little, well, yeah, we need to do a little work to get to v. Okay. So we got sine squared x dx. What do you think we should change that to? Okay, what is it? Okay, so 1 minus cosine 2x over 2. That's actually going to be our dv, right? Okay. And so we've got to integrate there to figure out what v is. Okay. So v could be 1/2 x from this piece, right? And then if we've got minus cosine 2x over 2, then that's going to be what? Okay. Minus sine 2x over 4. Is that right? Okay. All right, so that's our v. Okay, so all of that kind of goes over here to the side. Okay. Okay, so we get this is udv, so it's equal to uv. So uv was x squared times 1/2 x minus sine 2x over 4. So that's uv minus the integral of v du. Okay, so v du is 1/2 x sine 2x over 4 is minus sine 2x. Okay, that's v. Du is what? 2x dx. Okay. All right, so we get 1/2 x cubed, okay, minus, and that part we don't even really have to worry about right now, but minus x squared sine 2x over 4. Okay, and then we're integrating still. We've got minus 1/2 x times 2x dx is just going to be what? X squared dx, very good. And then plus sine 2x, let's say 1/4 the integral of sine 2x times 2x dx. Okay, is that right? Okay, we can cancel the 1/4 and the 2, so we're left with the 2 down here. Okay, so the integral of x squared dx, we can figure that out, right? That's easy. That's just what? The integral of x squared dx is x cubed over 3, okay? All right, but what about that 1/2 sine 2x times x dx? What do you think we're going to need to do with that? Okay, is there something that we could choose to be u? Okay, all right, if we chose 2x, then the derivative of 2x is just what? Just 2. And so we still have this x out here, right? So that doesn't work. All right, so what do you think we might need to do? The thing you don't want to say is what we got to do. We got to integrate by parts again. Okay, but just on that little piece. Okay, so we're going to use integration by parts a second time. Okay, integration by parts a second time. So we're integrating, and if you'll allow me, I'll just kind of come over here and do it. We're going to be integrating 1/2 sine 2x times x dx. Okay, so work on that at your desk on your own, and then we'll come back and look at it together. Okay, so what do you let u equal? 2x? The whole thing? If we're going to do integration by parts? Okay, the 1/2 x or just x, right? Because we can pull the 1/2. Remember the little acronym we had? Okay, we said log functions first, inverse functions, algebraic, trig, and then exponential. This is how we decide what u is going to be. Okay, so let's let u equal x. Okay, then of course du is just going to be dx. And then dv is going to be sine 2x. Okay, and so v ends up being what? Okay, very good. Negative cosine 2x over 2. Okay. All right, so when we do our substitution, still writing over here, but we got the 1/2 going along for the ride. Okay, and it's going to be 1/2 uv, so that's x times negative cosine 2x over 2. Okay, minus the integral of v du. So that's negative cosine 2x over 2. And now du is just simply dx. So that's going to work out great for us. Okay. All right. So looks like I can, well, let me integrate this first. This is going to be 1/2 negative x cosine 2x over 2. Okay. And then we're going to get plus sine 2x. Okay, and that would be over 2 times the 2 that was already there. So 1/2. Okay, plus c. Okay, everybody okay with that? All right, so if we clean that up a little bit, looks like I can pull another 1/2 out. So we get 1/4, okay, times minus x cosine 2x. Okay, and then we still have sine 2x over 2. Okay, plus c. So we need to take this back up there. Okay. So we get plus 1/4, or I guess I could say minus 1/4 x cosine 2x. Plus sine 2x over 8 plus c. Okay, questions about that? Okay, very good. All right, well, we have some similar rules for secant and tangent. Okay, they're on the next page there. They tell us if we have an even power of secant, then we're going to convert those to tangents. Okay, and we're going to hold on to 1 secant squared for the du, because remember the derivative of tangent is what? Secant squared. Okay, so we want to hold on. If we're going to convert everything to tangents, we need to hold on to some of those secant squares. Okay, if we have an odd power of tangent, then they tell us that we should convert. What are we doing? We're going to convert the even power to secant. We're going to hold on to one of those tangents for our derivative, okay, and so forth. All right, so those are the rules that we'll be looking at. Okay, they're right here and also in your handout. All right, so we got the integral of secant to the fourth 2x dx. Okay, this is going to be equal to, since I've got, according to my rules, I've got an even power of secant, I'm going to hold on to a secant squared. Okay, let's say this is it. Well, it doesn't matter which one. Okay, I'm holding this for my derivative. All right, holding on to that. So I can change the other secant squared 2x to what in terms of tangent? Okay. Well, that's another one of our Pythagorean identities. And it's 1 plus tangent squared 2x. Okay, everybody knows sine squared theta plus cosine squared theta equals 1, right? Okay, and so we could always either divide by sine or cosine to get the other two trig or Pythagorean identities. Okay, in case you don't remember, let me show you that just for the record. So we know sine squared theta plus cosine squared theta equals 1. So if I divide through, I'm trying to get tangent, if I divide through by cosine squared theta, we get what? Tangent squared theta plus 1 equals secant squared theta. Okay, so the only one I remember in the middle of the night is this first one, but I can get to the other two by dividing. So those are things, I'm saying all that and showing you that because I will not give those formulas to you on the test. Okay, so make sure you know that. Okay, so 1 plus tangent squared 2x, and then I've got secant squared 2x dx. Okay, so we got secant squared 2x dx plus the integral of tangent squared 2x secant squared 2x dx. Okay. All right, well, if we need to, we can say that u is equal to 2x for this piece, and du would be 2 dx, or du over 2 equals dx. Okay, so what we have here is the integral of, let's see, what do I have? Mm, Actually, no, what are we going to do? What should we let u equal? Or do we even have to do it this way? The derivative of tangent is what? Secant squared. So this right here, we can just look at it. Okay, the derivative or the integral of this thing is just going to be tangent 2x over 2. Right? The derivative of tangent is going to be secant squared u du. And so that'll get it for us. All right, but then over here, we've got the integral of tangent squared 2x. I might let u equal tangent 2x. Then du is secant squared 2x dx. Okay. Times 2. So du over 2 equals secant squared 2x dx. Okay. So we're going to say u squared, and then secant squared 2x dx is du over 2. Okay, and of course, that integrates as u cubed over 3 plus c. So this is going to be tangent cubed 2x over 6 plus c, and then we already had tangent 2x over 2. Okay, questions about that? Any questions? All right, very good. Okay, what about tangent cubed? Looks like I might have changed this in my notes. And let's change this to a 6. Okay, change that to a 6. Okay, then since we've got an even power of tangent, then what does it say we should do? In rule number 3, it says what? Okay. All right. So what I'm going to do is pull off tangent squared. Still integrating. And then we've got tangent to the fourth power, 3x dx. Okay? And now, what can we write tangent squared 3x as? Very good. Okay? Equals the integral of secant squared 3x minus 1, okay, times tangent to the fourth 3x dx. Okay, and so when I distribute, I get the integral of secant squared 3x times tangent to the fourth 3x dx. Okay, minus the integral of tangent to the fourth 3x dx. Okay. All right, so we got two nice integration problems here. This one looks really nice because we can let u be what? Or just tangent 3x, right? Because du would be secant squared 3x times 3 dx. Okay, so that one's pretty straightforward. When we integrate that, since this is d, we got 1/3, okay, times tangent to the fifth over 5. Okay, is that okay? And then we're left with this thing, which pretty much puts us back where we started, right? We've got tangent to an even power, raised to an even power. So what did we do before? We're going to break it up. So the integral of tangent squared 3x times tangent squared 3x dx. Okay, we're going to change one of those tangents into what? Okay, secant squared 3x. Okay. All right. It was secant squared 3x minus 1. Then we distribute. So minus the integral of tangent squared 3x secant squared 3x dx minus the integral of tangent squared 3x dx. Okay, so we got to do that part. And so this piece is pretty simple, I think. We'll let u be tangent 3x, and here's our du, secant squared 3x dx. So this is going to end up being what? We got the same substitution that we used up here. Okay, so tangent cubed 3x over, did you say 9? Y over 9.
Allow the 1/3. Derivative is secant squared.
Yes, over 9. Very good. All right, excellent. Okay, over 9. All right, and then we still have minus the integral of tangent squared 3x dx. What are we going to do with that? We got to do it just one more time. One more time. This is the last time. Okay, tangent squared 3x dx is what? Secant squared 3x minus 1 dx. Okay, so just to keep up with things, we got this tangent to the fifth 3x over 15 minus tangent cubed 3x over 9. All right, and then here we're going to have the integral of secant squared 3x. Well, that's just what? Minus tangent squared, or rather minus tangent 3x over 3. Is that right? We're still doing that same substitution. I mean, our u is pretty much tangent 3x du is secant squared 3x dx. Okay. And then we got 1 dx, so we can say plus x plus c. And that's our answer. Questions about that?